In this example, our goal is to find an equation for the moment of inertia of a certain object, a rigid hollow cylinder. So we want to find the moment of inertia knowing that the inner radius of our object is r1, the outer radius is r2, the height is h, and the mass of our object is given by the letter m. Now, notice we're making the assumption that the density of the object given by the Greek letter rho is constant. So the mass per unit volume of the object is constant. Now in a textbook we can find the volume of our object. The volume of the object is given by the following formula. The volume is equal to pi times the height multiplied by the difference of the squares of the radii. So r2 squared minus r1 squared times pi h, where r2 is the outer radius, r1 is the inner radius of our object, and h is the height of that object. Pi is simply our constant, 3.14. So we're going to need to use this equation in just a moment. First, let's discuss the approach that we will take in solving our problem, in deriving our equation. So our approach will involve dividing our rigid hollow cylinder into very thin concentric rings of width or thickness dr. So infinitely small change in our radius. So here's one such example of a thin concentric ring that has a radius r. So the radius r is between r1 and r2, a thickness of dr, infinitely small change in r, and a height which is not shown here but is shown here, a height of h. So we're dividing our hollow cylinder into many of these types of concentric rings. And at the end, to find our moment of inertia, we're simply going to take the integral. We're going to add them up. Now, let's begin by trying to calculate what our density of this ring is. Recall, density is equal to mass divided by volume. Now, what exactly is the mass and what is the volume? Well, because we're dealing with an infinitely small thickness, that means the mass is infinitely small and the volume is also infinitely small. So our rho, our density, is equal to dm divided by dv. And we can rearrange and solve for the mass and get the following result. So dm, infinitely small change in mass, is equal to our density multiplied by infinitely small change in volume. Let's call this equation 1. Now, what exactly is the infinitely small change in volume? Well, volume of such a ring, such a concentric thin ring, is given by the following equation. Circumference multiplied by thickness multiplied by height. So height is h, thickness is dr, and the circumference is 2 pi r. So now let's call this equation 2 and plug equation 2 into equation 1. Why? Well, because we're essentially replacing the dv term with this entire term, because this term is equal to dv. So we plug 2 into 1 and we get the following result. The infinitely small mass of such a thin concentric ring with a thickness of dr is equal to 2 pi multiplied by our density multiplied by the height multiplied by the radius r multiplied by dr. And let's call this equation number 3. We'll need to use this in just a moment. Now, before we go on, let's recall what our moment of inertia of such a thin concentric ring is. So the moment of inertia of such an object is equal to m times r squared, where m is the mass of that object, r is our radius of that object, and we squared that. So this is the moment of inertia of a thin ring, which we spoke about in a previous lecture. So now we want to calculate what the moment of inertia of all of these rings are that compose our hollow cylinder. So we want to take all of these rings and sum them up. So that means our moment of inertia is equal to the integral of r squared multiplied not by m, but by the mass of this one single ring, dm. And we want to take the sum, we want to take the integral. So now we note that dm is equal to this entire value. So we take equation 3 and we plug it into the dm value here, and we get the following equation. Now we're taking our integral with respect to r. So we no longer have dm, but we have dr. And we take it from r1, from the inner radius, to r2, to the outer radius. So we integrate all of these concentric rings. So let's combine all these values and take the constant and bring it on the outside of the integral. We get 2 pi, our rho, the density, multiplied by height, and we take the integral from r1 to r2 of r cubed dr. So we actually integrate. This becomes r to the 4th power divided by 4, and we evaluate the integral. We get the following result. So notice we get a 4 on the bottom, and there's a 2 here, so the 2 cancels, and the denominator becomes a 2. So we have pi rho h divided by 2 multiplied by r2 to the 4th power minus r1 to the 4th power. Now we can represent this quantity in the following mathematical notation. So r2 squared plus r1 squared multiplied by r2 squared minus r1 squared. So if we multiply these two out, we get back this quantity. So these are exactly identical. Now, because mass is equal to our density times volume, note that we can take this volume that we spoke of earlier and plug it into the volume here. So the mass of our object, our hollow cylinder, is equal to its uniform density multiplied by its volume, this quantity. So we take this and plug it into the equation, and we get that our density multiplied by pi h multiplied by this is equal to the mass. Now, notice that mass appears on this term. Or actually, mass doesn't appear on this term, but what does appear is, well, we have the rho, we have the pi, we have the h, and we have one of these terms, which is here. So we can combine them and substitute for this entire term. We can replace it with m, and we get the following result, that our moment of inertia is equal to m divided by 2 multiplied by, so we're left over with this value. So r squared to the 2nd power, or r2 squared plus r1 squared, where m is this entire value which appears in this equation. So this and this are exactly the same. And this is our formula, our equation for the moment of inertia, or the rotational motion of a rigid hollow cylinder with uniform density.